Right, the other day when we were speaking, we spoke about electrostatics. Can anyone tell me what it was about? Static electricity, non-moving electricity. So it has to do with static electricity. That is non-moving, non-flowing. It's not in a current. Doesn't mean that the electricity can't move at all, but it's not flowing through a conductor like normal electricity would that we normally know. Okay, what's the opposite, not the opposite, but what's the other type of electricity that we deal with? Current electricity. And that is flowing through a conductor. We normally have a battery to drive that current, etc., etc. Now, what is it that flows? Electrons. Is it always electrons that flow? Yes, I suppose so. In these fluorescent tubes, there's something happening in there, do you agree? Are those electrons that flow? In neon tubes, are those electrons that flow? So electricity is not necessarily the flow of electrons, or the movement of electrons, or the collection of electrons, but the collection of charge. So electricity involves either the collection or movement of charge. Okay, this we're going to be dealing with now. Static electricity and current electricity we will be dealing with later. But whether it is current electricity or whether it is static electricity, they all deal with charge. Static electricity, the charge tends to collect on one spot and stay there until it's able to move. And then it normally gives a little bit of a spark or a shock or whatever when it does that. Current electricity is the stuff that flows through the wires when you're listening to your music, when you're drying your hair, when you put a light on, etc., etc. And we said most times it involves the flow or the collection of electrons, but it doesn't have to be electrons. It involves the collection of charge. Right. And then we got to the stage last time we met was, what is charge? And scientists don't really know what charge is. We know that there are certain particles that carry charge. What are the two types of charge that we're aware of? You get two types of charge. Positive and negative. Right? What do you mean by positive? Okay, that's now because you understand it. But let's say you had never heard of a proton or electron before. You would know that if I charged two objects with the same type of charge, what would they do to each other? They'd repel each other. So if you put this particular type, let's call it a black charge and a black charge instead of positive or negative, okay? So if I gave it a black charge and a black charge, what would these two things do? They would repel, okay? But if I charge the one with a red charge and the other one with a black charge, what would they do? They'd attract. Or if I had two of them with red charges, they would repel, they would repel. Okay, so scientists said there are two types of charge. If I put the same type together, they seem to repel. If I put the two opposite types together, they seem to attract. What should we call them? So they could have decided on various names. They could have said, let's call it Alwetu charge and Ermelo charge. And if you have Alwetu and Ermelo charge, what will they do? They will attract. But if I have two Alwetu charges, they will repel. And if I have two Ermelo charges, they will repel. Okay? Or they could have spoken about red charge and black charge. Has anyone ever seen charge? No. What would be another way of talking about charge? Up and down? You get up charge and down charge? Would that be one way of describing two different types of something that you've never seen? You know they're different, but you're not too sure what they're. Give me another way of doing it. We know obviously positive and negative was how they settled on it. What? North and south charge. Same with magnets. Okay? North and south, really, if you look at a magnet, it's got nothing to do with north and south. Okay? But that's how we've labeled a magnet. We know that the two poles of the magnet are opposite, so let's call the one pole the north pole, the other one the south pole. Another way that you could maybe left and right charge? Would that be one way of describing two opposite types of charge? Okay, so they settled on positive and negative charge. But no person has ever seen charge. Okay. Later on, they discovered that this charge is found on certain particles. So certain particles carry the charge. Give me an example. Electrons. We abbreviated them E negative. Carry a negative charge. Okay. What makes them negative, we don't know. Okay. Protons. P positive. Carry a Are there any other particles that we know of that carry charge? Neutrons are neutral, so they're not charged particles. Do you agree? Okay, so neutrons don't carry charge. Electrons do, protons do. Alpha particles. They carry a what? A positive charge. It was later discovered that an alpha particle is actually a helium atom. How many electrons does a helium atom normally have? 2. How many nucleons? 4. And it's lost both of its electrons. That is actually what a helium, an alpha particle is. Okay? It's a helium nucleus. It's lost its 2 electrons. It's just the nucleus. We've also discovered that certain ions carry charge. And what charge do ions carry? Negative. Oh. And positive. Or all positive. Ions can be negative or positive. They can't be both at the same time. So they can be positive or negative charge. Give me an example of a positively charged ion. Let's keep it simple. Na positive. Okay, happy? Negative? Cl minus as an example there. Right, so there's some particles that carry charge. Okay, Now, which of these four types of particles, electrons, protons, alpha particles, and ions, are the genuine charge carriers? Electrons and protons. Because if we look at alpha particles, what are they really? What does it really carry here? What is it lost? Let's draw an alpha particle. It consists of how many protons? So it's got a P positive, we'll put it there, and we've got another P positive, we'll put it there. How many neutrons? 2, so let's draw them in blue. Neutral with a 0 to show that it's got no charge. Neutron with a 0, all happy. There's your nucleus. What does it have buzzing around it normally? It's got 2 electrons buzzing around it. We'll draw the one E negative and the other one E negative. Okay. Now, that's helium. But helium 2 plus, what has happened to it? It's lost its 2 electrons. So that's your alpha particle. Really, is it anything different to what you've already got on the table? It's the protons which are giving it its charge, isn't it? It's not anything new. It's not a different type of thing that's carrying charge. Okay? If we look at a sodium positive, what does sodium positive contain? Well, it contains how many protons? Sodium is Na1123. So how many protons? 11 P positives. How many neutrons? 12 neutron neutrals. How many electrons? Normally, how many would it have as if it was just sodium? It would normally have 11 electrons. But if I make it sodium positive, it's only got 10 electrons. That there. Okay. So is there anything new in a sodium positive that's carrying electrons other than electrons and it's carrying charge other than electrons and protons? No. Let's do the same exercise for Cl minus. Cl is 17, and let's write 35 up there. Right, what has that got? How many protons does it carry? It carries 17 P positive protons. How many neutrons? How many? 18 neutron neutrals. And as it is there, how many electrons? 17 electron negatives. What does this add up to? 0. But if I want to make this a Cl minus, I've got an extra 18th electron, and that now makes it negatively charged. Have I got any new types of particle here that are carrying charge, or is it just the same old electrons and protons still? Okay, so really, these are our genuine charge carriers. Do you agree? Everything else is just an amalgamation, putting them together like Lego blocks. Yes? No? Okay. But that's not true. Scientists at one stage thought, right, once they discovered electrons, they actually discovered the source of negative charge, the electron. Great stuff. And protons were the source of positive charge. It was only later that scientists discovered nonsense. You can take an electron and a proton and you can break them down, and you get 3 types of particle. And those particles were called quarks. Okay? And you've got 3 types of quark. You've got green quarks. They're not really green because no one's seen them, so you can't tell whether they're green or not, but that was the way they labeled them. They could have called them Christopher quarks. They could have called them Jonathan quarks. And they could have called them Richard quarks. 3 different types of quark. Instead, they decided to call them green, blue, and red quarks. Now, The interesting thing is if you took a green and blue and put them together, what did you get? You got negative charge. You got an electron. Okay. If you took green and red, you got neutral. And what are the remaining two? So you could make up protons. So this was a proton. Sorry, this here is an electron. Electrons are made up of green and blue quarks. Neutrons are made up of green and red quarks. And protons are made up of red and blue quarks. So, which are the things that carry charge? Is it the quarks that carry charge? Because a quark on its own has got no charge. But when you combine quarks, you can create charge. Okay. Scientists then took it a little bit further, and a few years later they were able to split quarks up. And they realized that you can break the quarks down. And you can break those things down, and you can break those things down. So where does charge actually start? We don't know. Okay, it's just one of those things. Charge somehow is there. We don't know what it is. We know what effect charge has, but we don't actually know what it is. Okay, so no one really knows what charge is. We can tell you a lot of things about it, but that's about it. Right, I don't expect you to know this. It's not necessary, just to fill you in. No one really knows what charge is. We do know what charge behaves like. Right, can we take this off, seeing it's not necessary? Yes. No. On its own, a green quark carries no charge. It's only once it combines that it suddenly has charge. Okay, but on its own, it's got no charge. It's neutral. Well, wouldn't know if it's neutral, but it's not even neutral because you could combine two quarks to get a neutral. When you get to electrons and protons, yeah. Okay, but is that really the source of charge, or is it that we don't quite understand it and we just don't know what's happening before that? Okay, so we don't really know what charge is. We do know which particles carry charge and how these particles behave. Right. Then we've got a formula for charge. So we always put a formula together. It makes us feel happy as science people if we can put a formula to something. Okay. Q equals I times delta T. Can anyone tell me what Q stands for? Q is charge. And what is charge measured in? Coulombs. Thank you. I is current, and it's measured in amperes. Delta T is time that has gone past, and that is measured in, how do I abbreviate seconds? Small s, that it? No EC, just small s, please. Okay. Can we give you an example or two? Coulombs can be both a capital and a small c. You'll see sometimes they use a capital and sometimes a Q. Are you talking about coulombs for the abbreviation for the charge? Coulombs is a capital C. Okay? The Q, grade 11s, that Q can sometimes be written as a capital Q, sometimes it's written as a lowercase q. Doesn't matter. But for coulombs, that's a capital C. Okay? Coulombs is a capital C. If you had to write, so that is coulombs. Notice how I write the word coulombs. Lowercase c. Okay? Where does the word coulombs come from? It's the surname of the person who discovered all of this, Charles de Coulomb. Okay? He spelt his surname with a capital C, but when we use it as the unit and you write it out, you spell it with a lowercase c. Okay. As a matter of interest, what does that stand for in science? Newton's, named after? So Isaac Newton. How did he spell his surname? Capital N. How do we write it if we write out Newton's? Okay. And what is a small c? That's the speed of light, the velocity of light, which is 3 times 10 to the power of 8 meters per second. So if you write a small c, it doesn't mean coulombs. Okay? Rather just write out coulombs, but capital C. Can also be concentration, yes. It depends on the context. If you're talking about physics and light and all of that, then small c is usually the speed of light. If you're talking about chemicals, then it's concentration. But sometimes you can work with light and chemicals together. Certain chemical reactions give off light. Certain chemical reactions are like start going if you shine light onto them. Okay, right. Let's just get back to this. How do these particles behave? Anyone tell me? Positives and negatives. What's the basic rule for how they behave? Like charges repel. And unlike charges attract. That's nothing new that you've known about for a long time. Right, can I give you some examples? Right, do that one quickly, please. Right, there we go. Let's mark the first one. Jonathan, will you tell me how to do it, please? Lang, Jonathan. Yep. Okay, so you said I is 12, yes. Why did you times it by 60? Okay, and you got 3, 6. What? Cooler. There we go. Good. Could you do the next one, please? Let me just remind you of formulae that you worked with earlier. That says power equals V times I. Voltage times current. What is this? That is power. That is voltage. Okay. Mila, will you tell me what to do? I equals P over V, right? I'm not going to change the formula around yet. Right, substitute. Okay, so you're saying P is 100, V is 220, and if you then say I equals 100 over 220, you work out that I equals, what does that come to? 100 over 220 equals 0.45 amperes. All happy with that? Right, that's a little sub-calculation that you've got to do first, isn't it? Now what are you going to do, Nikita? Next stage? Q equals I delta T, yes. 0.45. So 2 hours times 60, to bring it to minutes, you agree? Times 60 again. Okay. What does that work out to be? 3,240 coulombs. Good. Recurring, then you would have got a slightly bigger answer. That's fine. Yeah, no problem. What happens when we work out marking memoranda, we work out a minimum and a maximum. Your answer's got to be within it, provided you have done your working correctly. Okay, right, we're all happy with that. Next thing that I want to look at, if I can find my green pen, can anyone see it anywhere? Did I put it in my pocket? Oh, here we go. Right, is something called the electroscope. It's not in your syllabus, but I think it's important that we cover it. Who of you have seen an electroscope? Right, I'll show you one tomorrow. You've seen one, Ermela? What size is it? Big, big. The rod and the silver ball around it that makes your hair stand up. And no, that's the Van der Graaf generator. Okay, an electroscope, I'll draw it life size, okay? That's about the size of an electroscope. Right, now I'm going to draw it a bit bigger so that you can all see it. We've got one in the cupboard. Unfortunately, and that's the problem with the electroscopes, I'll tell you what they're made of in a moment and you'll see why they're so flimsy. They always break. It's blue, yes. Okay. If we have a look at it, we'll enlarge it in our sketch. Basically, that is almost what the electroscope is entirely about. Okay? What you do attach to it is a strip of gold foil. Now, who of you have ever seen gold foil before? It's about 99% pure gold. Can you tell me about gold as a metal? Is it a hard metal, soft metal? Gold is soft. Okay, if you have pure gold, you can never make a gold chain that's 100% pure. It will just break. It's far too soft as a metal. It's not like putty or marshmallows, but it's a soft metal. You know, some wire you can bend easily. Gold would be like that. So if you had a chain made out of pure gold, it wouldn't last very long. That's why you never get 100 karat gold. It's always mixed with other substances to make it harder and stronger. Yes? Those gold blocks they should be as pretty close to 100% as possible. Okay, so if you take your nail and you scrape it, you'll be able to make a scratch on it. Okay, that's why people, you see the athletes, what do they do when they get their medal? The idea is you should be able to make a mark on it with your teeth. Don't ask me why they want to do it, but it's now become the thing to do, sheep. But that's how you would, in the days past, If someone gave you a gold coin, yeah, soft probably is gold. Not a guarantee, it's probably lead as well. Lead's also soft. Is gold a heavy metal or a light metal? Extremely heavy, even heavier than lead. Okay? Now, what this consists of is a metal disc, normally about that size, the size of a big 5 Rand coin, the old 5 Rand coins. A metal rod that runs down, and a piece of gold leaf over there. Now, gold leaf, one of the things about gold is that you can roll it like dough into thin layers. If you were to take a sheet of gold foil that size, you buy gold foil in like little notepads. That comes on paper, like on tissue paper, and you take the whole page up, and you put the tissue paper down, and then you slowly pull the tissue paper away and the gold foil stays behind. Okay, now you've seen the lettering on our honors boards. That's done with, they paint the names in glue, then they take gold foil with tissue paper, put it on, and then blow the gold off. And the gold that's stuck to the glue, that's what you see. So it is actually genuinely gold. Your name is up in gold. But if you were to take a sheet of gold foil and put it in your hand, and put your other hand over it, and do that, you'd see nothing. The gold would disappear. It's so finely rolled that when you twist it, those little gold atoms roll up into tiny little balls and just fall away. Okay? So it's so thin. It's really flimsy. And this little strip over here is gold foil. So 9 times out of 10 you use it once or twice and it breaks. Okay. They usually put it in a box so that the drafts don't break that gold foil. So it comes in a box, little glass or a metal box. It's got a glass window on both sides so that you can see what's happening inside it. And also there's a little insulating washer there so that this rod doesn't actually make contact with the gold box itself. The rod is insulated. Now, what would happen if you were to charge this metal plate negatively? What would you be doing? You'd be giving it extra electrons. Where would those extra electrons go? Would they just stay there? They'd run down the rod as well, wouldn't they? Where else would they go? Onto the leaf. What would the leaf and the rod do if they both got negative electrons on them? The leaf lifts up. Okay, and you can see how it's charged. We'll talk more about this tomorrow. Thank you.